Good morning, dear learner. I welcome you all to the next lecture today. Here, Professor Ravi Kumar, School of Mechanical Engineering, Sastad University. Today, I am going to introduce you about the Propeller Aerodynamics. The main agenda will start from what is the purpose of propeller, how many types of propellers are there, what are the different geometrical parts of a propeller, and we'll enter into the propeller aerodynamics. So, as we look at the propeller, either a piston propeller aircraft or we can say the turboprop aircraft, propeller will be mounted right at the front part of the engine. Now, some of the propeller driven aircraft will have a single pair of propeller. That means one single blade consisting of uh, means one hub consisting of two pair of blades, and some turboprop aircrafts will have four total blades, right? If you look at this one and this one, four propeller blades attached to a single hub. Now, depending on the power requirement, one aircraft may have uh, one engine or may have multi-engine. So this is an example of multi-engine turboprop aircraft where total four engines are mounted, two on each side of the wing, having four bladed propellers. So the propeller is nothing but it is a rotating blade. Means if you look at the cross section of a blade, it is some sort of an airfoil shape. So a propeller blade can be resemble like an aircraft wing. So how an aircraft wing usually creates the lift due to the pressure difference between the top and bottom surface right of the wing, and one component of that lift basically in the case of propeller will generate the thrust, and the thrust will be responsible for making the forward motion of the object to which your propeller is attached. So it generates thrust based on the principle of rate of change of momentum. So generally we can say a propeller blade generates thrust through an aerodynamic lift force component, demands an engine torque to overcome the aerodynamic drag, particularly. Uh, so, so in order to counter the drag, it requires a torque, and torque is being generated right with the help of engine, and will stall if local resultant angle of attack of blade exceeds. So, if your aircraft is oriented at a very high angle of attack, at that point, at the tip of the propeller, there will be stalling. So, stalling means the propeller will not able to take in sufficient amount of air, and due to which the functioning of engine will deteriorate and engine will not generate the required thrust to sustain a steady flight. Additional factor to that is trailing vortex generation. This basically will happen when your propeller is flying at higher angle of attack. Tip losses due to the cross mixing of the flow, and compressibility, particularly if your aircraft is flying at a Mach number greater than 5, greater than zero point 0.5. That's what is the threshold value to decide for compressibility. How lift generate on basic airfoil? So a basic airfoil, when it travels through the free stream flow right regime, it creates the pressure disturbances. Right. So there is a pressure disturbance, and due to pressure disturbance, there will be unsymmetrical pressure distribution generated around the airfoil. So if we just focus on the top, means bottom surface, your streamlines are almost parallel. So there is less obstruction. So less obstruction means we can say that the what we say, this is the region where pressure remains almost constant. If we look at the top surface your streamlines are started. So as flow is taking place from our left right side to the left side, alright. So in that case, on the top surface it is having more curvature due to which there will be an accelerating flow when flow is getting accelerated. That means what? Velocity increases as per the Bernoulli's principle. When velocity is high, pressure will be less. So on the top surface, we'll have uh, negative pressure or low pressure compared to the bottom surface. As a result of this pressure difference, there will be a generation of lift. There will be generation of lift, right, which acts perpendicular to the free stream flow direction. So free stream flow direction is this, perpendicular that will get a normal reaction which is called lift due to the pressure difference between top and bottom surface. So greater is the pressure difference, greater will be the lift. So in order to generate larger amount of lift, right, you have to operate your airfoil at very fast rate to create more negative pressure on top surface. So if we look at the aircraft wing and propeller blade, by symmetry, right, by looking at geometry, both are the same. So this is the view when your propeller is functioning. One is functioning, it is basically looking like a disc which is actually rotating at certain RPM. So if we just focus on a single blade, right? So this is the propeller blade. If we look at the cross section, it's an airfoil and it's having a finite span. So it resembles like uh, a finite wing. So the flow over finite wing will be similar to the flow over a propeller blade. So apparent wing and propeller blades are similar in shape. When they are similar in shape, uh, they will be generating some sort of normal component of force that is called lift. So as in a propeller, we are having a pair of blades, maybe two or four pairs of blades. So the thrust will be a cumulative, effect of the lift generated by each and every blade, which are mounted on a hub. Uh, so so this is the thing when propeller is facing the flow is entering like this. This is the relative wind, right? So it travels over the surface and finally it gets separated, right, once stalling happens. So if we look at the propeller which is mounted on the nose of an aircraft engine, particularly we talk about the piston propeller aircraft where your propeller will be mounted on the front portion of the engine. So this is an airfoil, right, which is attached to the hub. So if we just focus on this line, this is called the center of rotation, right? About this, your blades will be rotating. So this is the hub, and this is the airfoil shape. So this is the relative wind direction, all right, and this is the direction which is showing the rotational velocity. So when they are rotating, they will be rotating like this. So velocity parallel to the plane of rotation is called rotational velocity, and as a result of these changes of velocity, you are getting the forward velocity by which your aircraft is moving on. So if we look at this plane of rotation, right, we are just focusing on there's a single blade. So how actually things are happening? Flow is entering from this side, right? Because this is the point which is facing the flow. So flow is entering from the leading edge, flowing over the surface. So when it's flowing over the surface, this is the region where we are getting basically the blade angle. So they will be tilted at a certain angle, or you can say the propeller blades are mounted on a hub at a certain angle in order to assess maximum amount of thrust. So or you can say a certain you know maximum amount of thrust to be generated from the blade symmetry or the combination of blades. So thrust direction is basically parallel to the free stream flow velocity by which your flow is entering into the rows of blades. So if vector pressure, basically as we know, as pressure difference increases between top and bottom surface, will have a large amount of lift generation. So the amount or magnitude of lift generation basically depends on the pressure difference between top and bottom surface. So as velocity is higher, right, particularly when your airfoil is traveling at 300 mile per hour, you will have a larger magnitude of a lift and is traveling at lower velocity. If we say 100 mile per hour, will have a lower lift. So this is the one way, either by increasing the velocity of the airfoil or velocity of the flow. If airfoil is stationary, we can generate, or we can generate, or we can reduce the lift. Similarly, if we change the inclination of the airfoil, we can generate larger amount of lift. So this is the position when your aircraft, your airfoil is basically inclined below stalling, angle of attack. We are having maximum amount of lift generation. Similarly, when it is oriented at relatively low angles, we'll have a smaller quantity of lift being generated right over the airfoil. So if we look at the propeller nomenclatures, how do we say what are different parts of a propeller? So if we look at this schematic, it's showing when propeller is rotating. So it is a pair of blades. So if we just focus on a single blade, this will be the cross section of blade that is called airfoil, and it will be basically attached to the hub. Center portion is called hub at certain angle, that is basically called pitch angle, by which you are attaching your F5 blades to the hub. So the center line, if we look at the center line of hub, that is called basically the shaft axis above which your uh, propellers are rotating, means propeller blades are rotating. So we just focus on this F1, we can draw it like this. So our shorter distance connecting the leading edge to trailing is called basically chord line, and this is the relative wind direction, right? Basically flow is entering like this, so this is the relative wind direction. The angle between the chord line, right, and the relative wind is called angle of attack. As I said that these blades are attached to the half at certain angle, that is called basically pitch angle. So this is the plane parallel to the half, and this is the inclination by which your blade is attached. So angle between the what do we say direction of rotation and the chord of an airfoil is called pitch angle, and this is basically total, it is making a circle. So this 2 pi r, or we can say 2 pi method, is basically the half diameter of the disc in which your blades are rotating. So this is relative velocity. Basically, this is the direction of relative velocity, right? This is called axial velocity, right? And somebody is asking, or what is the rotational velocity, that can be found out in this direction. It's called rotational velocity. So hub is nothing but the hub of propeller is a solid center disc to which short blades are attached. Either it is a one pair of blades or two pair of blades that will be attached to the hub. So ideally the hub should be as small in diameter as possible to obtain maximum lift. So if hub diameter is bigger, larger frontal area, that will invite larger production of drag. So overall thrust generated will be less. So in order to have a better design, hub should be a smaller diameter as possible. However, there is a trade-off between size and strength. So too small a hub ultimately will not be strong enough. So they have to decide based on the power generation or thrust generation requirements. Blades are twisted fins or foils that produce that protrude from a propeller hub. They are coming out from propeller hub, and the shape of the blades and speed at which they are driven dictates the torque a given propeller can deliver. Blade root and tip particularly be decide, like blade roots are the point which are attached to the hub, and tip is the outermost or a point driver flow is basically entering. The root of a propeller blade is where the blade attaches the hub, and tip is the outermost edge of the blade at a point, right, where flow is thus entering. Leading edge trailing edge. So if you look at the cross section of blade, there is an airfoil. So leading edge of a propeller blade or any foil is the side that cuts through the fluid. So fluid is entering through the leading edge, or we can say the leading edge is the something which is facing the below, and trailing is the downstream edge of the coil. Then they can further be classified like right-handed or left-handed propeller. So a propeller's handedness affects its shape. So right-handed propeller basically rotates clockwise when propelling a vessel forward as view from the front. Similarly, a left-handed propeller rotates counterclockwise as viewed from the stern, which is in a forward propulsion mode. So left-handed, right-hand, basically propeller decide based on the direction in which they are rotating with. So this is one example of contra-rotating propeller. A propeller basically rotates opposite to each other. So one propeller will be rotating clockwise, then another will be rotating anti-clockwise to negate the effect of additional torque generated on the wing, or additional torque being transferred to the aircraft with a single propeller. If single propeller is rotating, there will be additional torque acting on the aircraft, which will try to rotate your aircraft in, if this is a clockwise rotation, you will try to rotate your aircraft to the anti-clockwise direction. To negate that effect, uh, there is a design to attach the similar sort of propeller right at a similar distance away from the center of the fuselage to negate the effect of additional torque being acting on the aircraft. So it's called contra-rotating propeller. Either they may be two propellers attached at a different two direction, or there will be a combination of propellers, all right, on a single hub. If it is there is only one aircraft engine that is being used, that is especially for general aviation aircraft, will have a two pair of propellers, right? One propeller rows of blade will be rotating clockwise and will be anti-clockwise. This is an example of this combination, right, where two pair of propeller blades are attached on a single arm. So like these are three bladed propellers. So this was first row, this is the second row. So one propeller will be rotating clockwise, another will be going in anti-clockwise to negate the effect of torque being imposed on the fuselage. So this is the front propeller configuration. This is rear propeller configuration. Some of the aircraft is called pusher. Pusher means somebody is pushing from backside. So this is the pusher configuration, and this is called basically the conventional configuration. So propeller, if we look at for the pitch, so pitch is nothing but it is called a forward motion. An aircraft is going to cover in a single rotation of a propeller. So if propeller makes a propeller blade, if we just focus on a single blade, if that blade is going to turn around 360-degree, by that time, how much forward distance your object to which your propeller is attached is going to move is called pitch. Pitch. So actual distance is this, and ideal distance is this. If there's no losses involved, in that case, this object can travel from this point to this point without any hurdle. But in actual scenario, there are a lot of disturbances, means due to the downwards created on the propeller blades, your object or the aircraft would be able to travel only a distance up to this point, or actual distance. At this distance, which is called pitch. So the difference between ideal or theoretical distance to the and actual distance is called basically slip. So this is the slip basically. Then further, this pitch can be defined as coarse pitch or fine pitch. So coarse pitch is basically being said if your digits are attached at higher angle, that is called basically the coarse pitch. Fine pitch when your propeller blades are attached at small angle. So higher angle means it will be generating larger thrust, and smaller angle means it will be generating lesser thrust. So these are the different nomenclatures being used for defining the propeller. So how to analyze the propeller? So for analyzing the propeller, how much thrust is going to generate. So mathematically, how to estimate that? Some theories were developed independently. First is called disk actuator theory, or we can say the momentum theory, and second is called blade element theory, where blade geometries will also be considered, right, while assessing its performance, or assessing the performance parameters. So the first theory was came, that is called Froude's momentum theory. Froude is the name of scientist who developed this theory to analyze the propeller performance. This is also known as actuator disk theory. So it was originally intended to provide an analytical means of evaluating ship propellers, right? Particularly Rankine and Froude. These two fellows developed the theory and proposed the theory to analyze the performance of a ship propeller. So momentum theory is also known as discussion theory or momentum theory. So there are certain assumptions which were made, right, on a propeller to analyze its performance. So first is infinitely thin disk of area A, which offers no resistance to the air passing through it. So when propeller blades are rotating, right, they will be making a disk, and disk can be considered as infinitely thin of area A, which offers no resistance to the upcoming flow, or the flow which is passing through it. Second, the purely one-dimensional analysis. Third assumption, thrust, loading, and velocity are uniform over the disk. Fourth assumption, far upstream and far downstream, the pressure is free stream static pressure. So if we are going the farmost point, right, at the front of the hub, pressure will be standard atmospheric pressure, static pressure. So when you are going too much downstream, right, far away or far down, the pressure will be free stream static pressure. Fifth is viscous effects are not considered. So no drag, no momentum diffusion. Sixth assumption was incompressible flow. So compressive correction is not needed. So these are the six assumptions of this theory. So taking into these assumptions into consideration, they proposed a theory try to analyze the performance parameters of a propeller. That is known as Froude's momentum theory, or Froude's or actuator disk theory. So as per this, so this the disk basically. So this is the airflow where it's taking place. So this is the disk which is rotating. So this is the position of hub. So this is the velocity and pressure and density of the free stream flow which is entering into this disk, right? So upstream conditions are V, V naught and rho. The movement is entering through this disk, that is called disk velocity, right? This was the free stream airflow, right? The velocity by which it's entering into the disk is called disk velocity, V naught. Then this is the downstream condition, right? Downstream condition 2, where we don't know what is the velocity, what is the pressure, and what is the density. And far away distance, right? Let's suppose this call uh, safe stream velocity, right? And the pressure is standard static pressure or free stream pressure P naught, and front also it is P naught. So in unit time, if we are going to find out the mass of fluid passing through the disk, we can say the density area into velocity. So if we look at the disk, by the velocity by which fluid is entering is called V naught. So density into area into V naught, and look at this. So area front and back both are same, right? And this is very thin. So density area into velocity is called mass flow, which is entering through the disk. Second, so increase of rearward momentum of the mass flow. So mass flow entering, we can say rho s v naught, mass flow is leaving is called rho s vs. So if we find the momentum, right? So mass into velocity change. So this is the mass flow rate, and the velocity change between upstream and downstream is nothing but downstream velocity vs minus the upstream v. So the multiplication of mass flow rate into change in velocity is called increase in rearward momentum. So momentum is given by this equation, equation number 2. and rate of change of momentum is called thrust basically. So whatever momentum we got, that generates the thrust. So thrust on a disk is given by the mass flow rate and to change in the velocity. So rho as v naught, vs minus v is called thrust. Thrust can also be calculated via pressure difference between the upstream and downstream flow. So thrust can also be calculated based on the pressure difference. So P2 minus P1, where P2 is the pressure downstream of the disk and P1 is the pressure upstream of the disk. So the flow is seen to be divided into two regions, right? Particularly after the disk. First region is upstream, second is called downstream. So when we are applying the Bernoulli's principle to find out the pressures in upstream point 1 and downstream point 2, we have to apply the Bernoulli's equation with the point upstream of the disk at a point far away from the disk, right, called free stream flow, and similarly a point downstream of the disk and a point far downstream of the disk in order to get the pitch difference. So if we do so, we can write these two equations, right? This is called free stream conditions. P naught plus half rho V square equal to P1 plus half rho V naught square. So this is the upstream condition to the disk, and this is the downstream condition of the disk. If we take the difference of this, we can get P2 minus P1. So we can get P2 minus P1 given by this equation, half rho Ps square minus V square, or actually the pressure difference. So based on this, we can find out the thrust. So substituting this in equation number 4 and equating to equation number 3, we can have thrust equal to rho s v naught vs minus v. So we have replaced P2 minus P1 in equation number 4 via this equation, and we equated that to the equation number 3 of thrust rho s v naught vs minus v. So what we need to do? We divide throughout by vs minus v, right? We can solve it. So dividing this equation by rho s vs minus v, this entire equation, we can get the velocity by which flow is entering into disk is half of the slipstream velocity and free stream velocity. So this shows that the velocity through the disk is arithmetic mean of the velocities well upstream and in the fully developed slipstream. Further, this velocity can also be defined in some constant terms. The further velocity through the disk can be written as v not equal to free stream velocity 1 plus a. So Vh plus V, if we are writing Vh plus V, that will become 2 times of V naught. So V naught is given by V 1 plus A. So we can say this as 2 times of V 1 plus A, equation number 7, where slipstream velocity Vs is equal to V 1 plus 2A. Alright, so the quantity E is known as inflow factor. Quantity A is known as inflow factor. So the energy balance, if we find out on disk, energy is nothing but kinetic energy. So the kinetic energy entering and leaving, if we take the difference of this, we call energy balance. So energy balance, energy by time, can say mass flow rate into half rho v square minus vs square minus v square. This is slipstream velocity, this is of free stream flow velocity. So you can get the kinetic energy half mv square. Difference is called energy balance. So finally we are getting half rho as v naught vs square minus v square. This amount of energy is being developed, not developed, transferred by the propeller. So the rate of increase of energy of fluid is in fact the power supplied to the actuator disk. So now we can define the efficiency. So efficiency is nothing but thrust into velocity is the power available via uh, input. So input energy is this half rho s v naught vs square minus v square. This coming from outside incoming kinetic energy is getting converted into thrust. So thrust into velocity is called available power generated by a propeller by incoming, right? So incoming is kinetic energy which is entering. So that is known as ideal efficiency or propulsive efficiency of the propeller. So we can write the thrust equation as rho s v naught gs minus v into v Further simplification will arrive at this sort of equation of Vs plus P, right? Divide through or by V stream flow velocity, right? We can relate this in terms of inflow factor. So efficiency, power, and thrust in terms of inflow factor. So what we did here divided via divide and multiply by V stream flow velocity. We can write in this way 1 plus Vs by V, and substitute the value of Vs in terms of inflow factor A, right? Or just we know that the velocity by which flow is entering into this is basically the combination of this. So we means arithmetic mean of Vs plus V by 2. So Vs plus V by 2 can be said as V naught. So we'll have simple modification done here, right? And so we can get velocity divided by the velocity by which flow is entering into the disk. This can further be written as 1 divided by 1 plus A. So ideal efficiency of propeller is nothing but 1 divided by 1 plus A. So power is thrust into velocity divided by the efficiency. So propeller is having its own efficiency, so the actual power generated is called power available divided by the efficiency. So efficiency already we defined V by V naught. So power can be written as T into V naught. So where V naught already you know that is called V1 plus A, and this is the slipstream velocity. Vs is equal to V1 plus 2A. So thrust is nothing but mass flow rate into Vs minus V. So substitute the value of V naught here and Vs in terms of A. If we solve this, we can get thrust is equal to 2 rho S V square A 1 plus A. This is the equation of thrust. This is number 12. So figure of merit. The figure of merit is defined as the ratio of induced or ideal power to the actual power. So ideal power by actual power ratio is known as figure of merit. So figure of merit is given by this equation. So usually for ideal case, figure of merit is 1. That means induced power is equal to the actual power. But in most of the cases, it will be less than 1. So for a very good practical rotor, right, figure of merit will be equal to 0.8. Non-dimensional coefficients. So we can express these coefficients, right, like thrust coefficient, pressure coefficient can be defined from the traditional equation. So thrust coefficient is called thrust divided by rho A omega square. So omega into r, omega into r radial velocity square. So omega into r, this is omega, right, angular velocity. So we can say rho A V through square. So torque coefficient means torque divided by rho A into omega square into r. So these are radial distance, the perpendicular distance to the center of rotation, that is called radius of the disk. This is known as the torque coefficient. Similarly, power coefficient can be defined as power divided by rho A omega q, omega into r q. Or we can say that power divided by rho A VQ. So torque and power coefficients are further interrelated. So power is equal to torque into omega, or we can say 2 pi nt, which comes from this equation. So power coefficient is power available divided by rho A VQ. If you rearrange this, you can relate in terms of CQ. So pressure coefficient is equal to the torque coefficient. So what are the limitation of disk actuator theory? Whatever assumption we make, whatever left with, that is called limitations. So momentum theory doesn't take into the account number of blades. Nowhere we have taken the effect of number of blades. Airfoil characteristic like lift drag and zero lift angle of attack. These terminologies we have not used. This is also the limitation, right? Because we know that if we change the airfoil characteristics, we'll have to change the angle or zero lift angle of attack in order to change the overall thrust generation, right, through that airfoil. So next one is blade length form. We have not taken into consideration in this actuator theory, that what is the taper of the uh, blade, what is the sweep or root cutout, etc. Blade twist distribution also we have not taken into the consideration. Compressive effects also we have neglected. These are certain limitations of disk actuator theory. So this much is enough for today. So if you are having any doubt in this, feel free to write in the comment section, or you can reach out to me by my WhatsApp number. So thanks for your patience. See you all in the next class. Have a nice day. Good day.